To understand the failure of Chernobyl's Unit 4, we must reconstruct the physical architecture of the RBMK-1000 reactor core. Our forensic analysis isolates a specific terminal transient sequence. This sequence began at exactly 1:23:40 a.m. on April 26, 1986. The core itself was a massive vertical cylinder, measuring 11.8 meters in diameter and 7 meters in height. Unlike Western pressurized water reactors that house their core inside a single steel vessel, the RBMK distributed its fuel across 1,661 individual technological channels. Each of these vertical channels effectively operated as its own independent pressure vessel. Because of this immense scale and distributed architecture, uniform monitoring and control across the entire matrix was physically impossible during extreme power fluctuations. The fission reaction inside this core relied on the continuous interaction between two critical materials, solid graphite blocks and light water coolant. The graphite served as the primary moderator, slowing down fast neutrons emitted by the uranium fuel to successfully sustain the chain reaction. The light water, pumped upward from the bottom of the core through the channels, acted primarily as a neutron absorber rather than a moderator. This illustrates the positive void coefficient. When water turns to steam, its density drops, absorbing fewer neutrons. With the graphite moderator in place, these freed neutrons strike fuel rods, increasing reactivity. This generates more heat, boiling more water, creating more steam voids. This specific interplay of graphite and boiling water meant the reactor's physical architecture was engineered to accelerate its own power generation the moment coolant flow faltered. During the safety test at 1:23 a.m., operators closed the turbine stop valves. As the turbines coasted down, the main circulating pump slowed, heavily reducing the flow of coolant through the core. With less water moving through the channels, the coolant at the bottom of the core warmed rapidly, initiating premature steam void formation in the lower regions. Dictated by the positive void coefficient, this steam formation began silently adding positive reactivity to the bottom of the reactor. To evaluate how the core responded to this, we look at a stability metric known as the migration area to core height ratio. This comparison shows that standard reactors have a high enough ratio to allow power fluctuations to spread evenly. The RBMK had an exceptionally low ratio of roughly 0.020. Thermal fluctuations remained isolated in specific zones, leaving the core highly susceptible to severe spatial power oscillations. Because of this spatial decoupling, a power spike in one section was not felt or countered by control systems in another. The top and bottom halves of the reactor began functioning as isolated, independent nuclear environments. Earlier in the shift, the reactor had been operating at a reduced power level. This caused a massive accumulation of iodine-135 within the fuel, which decays directly into xenon-135. Xenon-135 is an extreme neutron poison. It possesses a massive absorption cross-section of 2.6 million barns, making it over 5,000 times more effective at absorbing neutrons than the uranium fuel itself. The decoupled nature of the core allowed this xenon to heavily concentrate in the upper half of the matrix, absorbing neutrons and effectively choking out the fission reaction in that region. To maintain the required power levels against this suffocating poison, the operators withdrew nearly all of the manual control rods from the core. This action depleted the operational reactivity margin down to roughly 8 rods, violating the strict safety minimum of 15. With the upper core poisoned and the lower core voiding, the removal of these rods left the reactor with no remaining safety margin to counteract a localized power surge. The final safeguard was the AZ-5 emergency scram system, designed to simultaneously drop all 211 control rods into the core to halt the reaction. The RBMK control rods were composite structures. They featured a boron carbide upper section designed to absorb neutrons, connected to a 4.5-meter graphite displacer tip. The intended purpose of this graphite tip was to increase reactor efficiency. When the rod was fully withdrawn, the graphite displaced neutron-absorbing water from the center of the channel, boosting reactivity. The graphite section was 1.3 meters shorter than the total height of the core. When fully retracted, this left a 1.25-meter column of liquid water pooling at the very bottom of the channel. Engaging the emergency shutdown from a fully withdrawn state required moving neutron-accelerating graphite straight through a zone of neutron-absorbing water. At exactly 1:23 and 40 seconds, the AZ5 button was pressed. The control rods began their descent into the core at a slow speed of 0.4 meters per second. This triggered the positive scram effect. As the rods entered the core, the 4.5-meter graphite tips plunged downward, physically pushing the 1.25-meter column of water out of the lower channels. In the xenon-free, highly volatile lower half of the core, replacing that liquid water with solid graphite instantly created a massive reactivity spike. Because the upper core was heavily poisoned by xenon, the boron sections of the rods were functionally useless as they descended through the dead zone. Pressing the emergency shutdown button acted as a mechanical detonator, injecting maximum reactivity precisely into the most unstable region of the decoupled core. The localized power surge was immediate. Within 3 seconds of the AZ5 press, thermal output in the lower core exceeded 530 megawatts and began doubling exponentially. The lower reactor core instantly achieved prompt criticality. In this state, the fission chain reaction is sustained entirely by immediate prompt neutrons, stripping away any possibility of mechanical control. The extreme instantaneous heat caused the uranium dioxide fuel pellets to fracture and shatter within their zirconium cladding. When this white-hot, fragmented fuel made direct contact with the liquid coolant, it caused a flash evaporation event. The sheer force of this instantaneous steam explosion simultaneously ruptured all 1,661 pressure tubes. The internal pressure lifted the 1,000-ton biological shield known as Elena, severing all remaining channels and exposing the destroyed matrix to the atmosphere.